All right, folks, we are back and we are now going to be studying 4.16 on Fisher's discriminant for multiple classes. So how we can extend those ideas of maximizing between class variance and within class versus within class variance to the case of having multiple classes. And I think the idea is, again, it's quite elegant. Um, this section is, again, purely computational. So I think the main thing to take away is kind of the approach to the problem. And there are references here that I actually recommend you look at for more details on this. It's actually quite an interesting problem, and the approaches to it are useful to look at. But we'll just kind of go through the computation in the section. Okay, so let's get started. So we now consider the generalization of the Fisher discriminant to k is greater than two classes, and we shall assume that the dimensionality d of the input space is greater than the number of classes, which typically will be the case. Next, we introduce d prime greater than 1 linear features, where k is 1 to d1. These feature values can conveniently be grouped together to form a vector y. Okay, so similarly, the weight vectors can be considered to be columns of a matrix W, so that y is equal to essentially the projection along those columns of a new data point. Okay, so the rows of W transpose are going to be these WKs, and you're going to project your data onto that. Note that, again, we're not including any bias parameters in the definition of y. Okay, the generalization of the within class covariance matrix to the class of k classes is, so this one's pretty straightforward. So you're summing up the class specific covariances, and these are just your normal covariance formulas, except they're missing a 1 over nk. So you think of it as like an unnormalized covariance, if you like, but all you're doing is you're just computing the covariance relative to the mean of a particular class, the class that the data comes from. So this would be like, we found it's the same idea as we had before. So if you've got like a class here, and maybe a class here, and you've got all of these points hanging out. Oops, that one should be red. So now you're computing kind of these covariances, how they're related to this point and how these guys relate to that point. And those could be different. They'll obviously in general have different shapes, but you then pool them, you add them all up. So that's your total within class variance. Now, in order to find the generalization of the between class covariance matrix, so this is the within class, we follow Duda and Hart and consider first the total covariance matrix. So this is basically the normal covariance you would compute for the data if there was no class labels. Like this is what you would compute in PCA, for example, where there's no class labels. You're just computing the covariance of your data. If we go back to our example up here, so I'm now going to make a little ball around that, and this would be kind of relative. These guys would all be computing relative to this mean point. Okay, so that's the total covariance. Again, there's no factor of n over here. It's just floating, but so just be careful about that. Where m is the mean of the total data set. Okay. So the total covariance, and this is a cool idea. So I think this idea of analysis of variance, analysis of covariance is like a really neat idea that comes up quite a lot in kind of these linear approaches in statistics. So the total covariance matrix can be decomposed into a sum of within class covariance plus an additional matrix SB, which we identify as a measure of the between class covariance. So I think this is effectively the most important, I'd say probably the most important idea here. Okay, so we've got an S total, which was this thing, is equal to the S within, which you've already defined up there, plus something that's left over. And it turns out that what's left over here is this quantity. So it's now going to be, so now you're going to replace, effectively what you're doing is you're replacing each point within each cluster with the mean of that cluster. So that's going to be, let's say, M2, it's going to be M1, and now computing the overall covariance of your new population, the total covariance of your new population when you've kind of reduced the points in each cluster to the mean. So that's what's happening here. So notice that now, again, so we've got, let's say, our particular cluster here, and there's some other one over there. One way you could view one way you could view this quantity here is, you could just write this as, well, this is some, I don't know, like n belongs to capital K of, mk minus m times mk minus m. Or maybe to make it actually even more explicit, kind of what we're doing, you could say we'll make a new, like a new version of xn minus m times xn minus m, where x hat of n is going to equal to the mean of the class of n, something like that. So effectively, you're just replacing, you're computing the total covariance of your data, but you're computing it after you map your points. You replace each point with its cluster, with its corresponding cluster mean. That's one way to think about it. And the way it comes out, again, you don't have to kind of guess this. It just came out of, you had your total covariance and you had your within class covariance. So whatever was left, you defined as the between class covariance. It's not exactly the same definition as we had in the 2 sample and the 2 class case. I think they're related by some constant factor of like n1, n2 over n or something like that. So they're related, but they're not identical. So in that sense, I think, yeah, just keep that in mind. Okay, but again, I think the key idea, which I think I want to kind of highlight, is this notion of defining, just this analysis of covariance, splitting up the covariance. Okay, these covariance matrices have been defined in the original X space, right? We can now define similar matrices in the projected d-dimensional Y space. We just project those things down, right? Exactly the same way. And all we've done here is we've just multiplied, we replaced all of these x's with their projections with that W matrix, right? So now we've now, so the xn has gone, so this x of n has gone to y of n, those means have gone to the means of the projections, etc. So this is the within class covariance, and this is of the project data, and this is the between class, again, of those labels. Now again, we wish to construct a scalar that is large when the between class covariance is large and when the within class covariance is small. And actually, if you read this Fukunaga reference, like I believe I read it once, he does consider various ways of doing it. Like I think he considers, like, what if you subtracted them? That was at least, I think, one of them. There were some other options too. And I guess one picks among these options by a combination of what's easy to compute, what gives good answers, what's practical, etc. So one example is given by, let's just highlight this point. So there are now many possible choices of criterion. One example is given by this, again, very similar to before. So dividing, we had that, divide the between class covariance by the within class covariance, trying to keep the between as large as possible and the within as small as possible. And you just replace these with their versions, before the projection. So the version where W is in there, and you get, so this is obviously coming from there, and this is coming from there. Maximization of such criteria is straightforward, though somewhat involved. Where the weight values are determined by those eigenvectors of this, which is, and keep in mind, this isn't a symmetric matrix, so the eigenvectors aren't going to be orthogonal, that correspond to the D prime largest eigenvalues, right? The ones that are going to have the large eigenvalues are going to be the vectors that are SB, that produce a large between class covariance at the same time as, and then I'm kind of speaking loosely here, at the same time as a small within class covariance. That's effectively what this is saying. So when you multiply that vector by SB, so you blow it up and then you divide it by the within class, it's really large. So I think this result is actually quite intuitive when you think about it that way. But the question is, knowing to characterize things, in this particular way. That's the trick. Now, the final paragraph, he talks about something. I'm not sure exactly, what. I can follow it up until nearly the end. So let's just say what he says. I'm not sure what he means by the end, but okay, let's just go. So there's one important result that is common to all such criteria, which is worth emphasizing. We first note that SB is composed of the sum of k matrices, each of which is an outer product of two vectors, and therefore of rank 1. Okay, so that's easy enough. So if we go back to S of B, sorry guys, where was it? Oh, here it is. Okay, so these are rank 1 terms, and they're not going to be identical, and they'll generally be linearly independent. So when you add them all up, you're going to get a rank k term. So this SB in general could be of rank k, but these mk's actually satisfy a property that if you do a weighted sum of them, they'll actually equal to m. So in fact, this structure itself, SB, has rank k minus 1. Okay, so that's so far so good. Only k minus 1 of these are independent as a result of the constraint 4.44. That constraint was this one, right? So that's just what I just said. Thus, SB has rank, and there are at most k minus 1 non-zero eigenvalues. So far, so good. Yes, so that's just, nothing wrong with that. So let's just, each of which is at rank 1. In addition, only k minus 1 of these matrices are independent as a result of the constraint. Thus, SB has rank at most k minus 1. Yes, and there are at most k minus 1 non-zero eigenvalues, which means the same thing. This shows the projection onto the k minus 1 dimensional subspace spanned by the eigenvectors of SB does not alter the value of JW. I guess maybe kind of talking about this, that if we kind of take the k minus 1 largest values, then this shows that the projection onto the k minus 1 dimensional subspace spanned by the eigenvectors of SB does not alter the value of JW, and so we are therefore unable to find more than k minus 1 linear features by this means. I'm not exactly sure what he's, I think I can get this aspect, because beyond that, you're not, like, SB itself is k minus 1 dimensional, so you're going to get at most k minus 1 dimensions and k minus 1 features. But I'm not too sure about this particular statement. So if you guys have a better idea of what he means, just please post in the comments so we can all learn and clarify this point. But I think, anyway, the main ideas of this section was, I think the key point was this decomposition, taking the total variance and decomposing it into a within class variance and using whatever is left as the between class variance. So sometimes when I try to rederive this kind of from memory, I forget that SB is just kind of what's left over. So that's how you define it, and then coming up with the criterion to maximize SB while minimizing SW. And again, it's not always clear what that criterion should be. The references show there are multiple options, but the one that is typically used, and the one used here, is maximizing, essentially finding the largest eigenvalues of this matrix. So so I think these references are actually good to look at. Look at Fukunaga; he's got a good discussion of this, and in Duda and Hart, the pattern classification book has some really nice pictures about what's going on. So I'd recommend that. But I think that's it. So I hope you enjoyed that. Please, as always, just give some comments about whether you did or you didn't. Any clarifications? Always happy about those. And next time we're going to talk about the perceptron algorithm. So hope to see you there. Bye.